Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking a 15 horsepower 230 voltage 1800 revolutions per minute shunt DC motor has full load armature current of 60 ampere when operating at rated conditions. The armature resistance of the motor is RA is equal to 0.15 ohm and the field resistance RF is 80 ohm. The adjustable resistance in the field circuit Radj may be varied over the range from 0 to 200 and is currently set to be 90 ohm. Armature reactions may be ignored in this machine. The magnetization curve for this motor taken at a speed of 1800 revolutions per minute is given in tabular from below. Okay, here we have the table. The first question is asking what is the speed of this motor when it's running at the rated conditions specified above. Now let's see how to calculate this one. A part, here we have Radj that's given to be given to be 90 ohm. And the field resistance, okay, we have 90 ohm right here and the field resistance is 170 ohm. Field resistance is 170 ohm. Field resistance 170 ohm. And IF is equal to VT over RF plus Radj. VT is 230. Field resistance, oh, I made a mistake right here. Field resistance is 80 ohm. Okay, it's not 170, it's 80 ohm. 80 plus 90 and that gives us 170. Altogether is 170. So 230 divided by 170. Alexa, what is 230 divided by 170?
230 divided by 170 rounds to 1.353.
So the current is 1.35 ampere. B part is asking the output power from the motor is 15 horsepower at rated conditions. What is the output torque of the motor? Now to find out the torque, here we have the power is given. There is 15 horsepower and the output speed is 1800 revolutions per minute and the torque is asked to be found. Torque out is equal to P out divided by omega in. Now P out 15 horsepower multiplied by 15 horsepower, that's power, multiplied by watts per horsepower. Let's see what do we have right here. 0.15, that is 15 horsepower multiplied by 746.46 watts per horsepower divided by omega. Omega is 1800 revolutions per minute. And if we want to convert this one for radians, we had to put 25 radians over 1 hour times 1 minute radians per second, 1 minute per 60 second. Okay, now when you calculate this one, you're going to get 59.4 Newton meter, and that is the torque. Okay, now the next thing is the third part is asking what are the copper losses and rotational losses in the motor at full load. C part, copper loss, copper power. Let's calculate the copper power. PCU. Okay, first we are going to calculate the copper. Okay, this one here 15 horsepower to 746 watts per horsepower. This is a conversion from horsepower to watts. Okay, that's what you have to know. And here we have 1800 to 25 radians over 1 over hour, 1 minute over 60 second. We are converting this revolutions per minute into radians per second. Now let's go to C part. C part is asking what is the copper losses and rotational losses in the motor at full load. Let's calculate the copper losses. Copper losses is Ia square Ra plus Vf times If. Ia square. Ia is 60 ampere given, 60 square times Ra 0.15 plus Vf is 230. Vf is 230, and then If is what we found out right here, that's 1.35 ampere, and that gives us 851 watts, and that is copper losses. Now the next thing is we have to find out the rotational losses. To find out the rotational losses, we had to find out the power that is converted from electrical to mechanical first. So the power converted from electrical to mechanic, to calculate that one, we use this formula EA times IA. EA, what is EA? We have at full load 1.35 ampere. 1.35 ampere, it is the EA current. Here if you look at the table, here we have 1.28, but our current is 1.35, so it's in the middle. And if you exactly found out like what's the difference, 8 to 4, 8 is difference. Here it's approximately 221. That's the one we are going to use right here. EA is 221 times IA is equal to 60 ampere. 221 voltage, and that gives us 13,260 watts. Now here we are trying to find P rotational, so we also have to find out the P out for that. P out is 15 horsepower, that's given. If I want to convert this one into watts, I have to multiply this one by 746 watts divided by horsepower, and this way we will get 11,190 watts. Therefore P rotational is equal to P converted minus P out. P converted is 13,260 watts minus 11,190 watts, that is equivalent to 2,070 watts. And that's it. Now let's look at the D part. D part is asking for the input power. D part is asking for the efficiency of the motor at full load. For this one, first we have to find out the input power. We already know the output power, that is 11,190. We have to calculate the input power, so we can find out the efficiency. To find out the input power, this is the formula: Vt times Ia plus If. Vt is 230 voltage multiplied by Ia, that is 60 ampere, plus If we calculated in the first A part, that's 1.35 ampere. That gives us 14,100 watts. So the efficiency at the full load, that is P out divided by Pn multiplied by 100%, that's equivalent to 11190 watts divided by 14,100 watts multiplied by 100%, and that gives us 79.4%. Okay, that is the efficiency. Now the E part is asking the no load, if the motor is now unloaded with no changes in terminal voltage of Radj, what is the no load speed of the motor? Now to find out the speed, we know that Ea is equal to 230 voltage if it's no load, because that's the one given right here. And so to calculate the no load speed, this is the formula: N is equal to Ea divided by Ea0 multiplied by N0. Ea is 230 voltage divided by Ea0. Ea0 we found out from the previous current. If you notice 1.35 from the table, that is almost 221 voltage multiplied by the rotational speed, that is 1800 revolutions per minute. And so if you calculate the no load speed using this formula, that will give us 1873 revolutions per minute, and that's the answer for the E part. And that's how we do this kind of problems. I hope you guys find this video helpful. Thanks for watching, and if you are trying to learn electromechanical system, there are a bunch of videos in my playlist. I hope you guys watch that too. Don't forget to subscribe. See you next time.